Future. Okay. Future human exploration on the moon is focused on missions to the lunar South Pole. Why is this the case? The story behind this current goal for lunar exploration starts in the early 1950s, when a prediction was made that water might accumulate at the lunar poles. Dr. Lawrence is going to tell the story of how this early speculation led to theoretical predictions of water on the moon. A detour takes one to the planet Mercury, and now, based on various Earth and spacecraft observations that started in the 1990s, the lunar South Pole is the target for the next human landing on the moon. So this is the story. The story takes place over 70 years. So there's quite a bit to talk about. So I'm going to stop.
All right. Well, thank you very much. And I, again, appreciate the reminder. When I saw the email, I realized that I was going to be in Japan, but the date actually worked out perfectly. Our flight got in 2 o'clock in the afternoon, and this is perfect to keep me awake. So much appreciated. Also, in terms of the topic, and I was reminded, a year ago when you gave the invitation, can I talk about Artemis? I actually don't work on Artemis. There's people at APL that do. In fact, there is a head of the Artemis 3 geology team is actually at APL. And so some of the tail end of the slides for this presentation I got from her, which are really nice set of slides. But really, since, I've done a lot of lunar science work early in my career, not Artemis now, but I thought telling the story of why are we going to the South Pole? What's the importance of that? And it's a pretty neat story with lots of twists and turns. And so I thought being able to share that with you would be a fun thing to do. Also want to say, if you have questions or anything, please jump in and just raise your hand or whatever. I'd be happy to stop and talk about that. I'd rather, get good information out rather than going through all the slides here. So, and I might be asking questions as well as we go forward. So, yeah.
So, yeah, you mentioned a South Pole, so that implies, so is it not, like some kind of, magnetic field? I mean, because the Earth is the moon is phase locked to the Earth.
Right.
Do we just assume that it's a pole because it sort of stays constant with regard to us, or is there actually some magnetic pole basis?
It's not a magnetic pole, it's geographic, it's physical, and I'll get into that somewhat. And that does play a role in, why we're going there. And, one of the main reasons, to jump to the chase, is we think there's good resources there for extended stays of human beings at, we say the South Pole, the North Pole also could be an opportunity for that as well. But it's not, so the moon doesn't have a magnetic field in the way that the Earth does. It does have isolated places with magnetic fields, but those are more localized. So the magnetic field doesn't really play a role in the story. So as I mentioned in the title, this is a 70-year story. Let's see. All right. There we go. So it actually goes back to a book by Harold Urey. I don't know if anyone's heard of Harold Urey. He was the guy that I think put together experiments with lightning in a box and trying to see if you can generate organic materials to simulate early Earth. Well, he also wrote a book called The Planets, Their Origin and Development. And this was page 17. And you can't read it, but I'll highlight some of the key words. Is what he suggested that there may be condensed volatile substances might be present near the lunar poles. And the reasoning behind this was that there may be craters at both the North and the South Pole that are cold enough, they never see light, and therefore they're very cold. And it was that insight that led to the idea that maybe there could indeed the volatile substances at the poles of the moon. Now, the reason behind this, and this sort of gets at this initial question. First of all, looking at the Earth, we all know that the Earth is tilted around 23 degrees on the axis. This is why we have seasons. So, you know, if you're at the Earth's North Pole here, during the summertime, you have constant sun at the north and constant dark at the south. And then when you change, you know, from north to south, the situation reverses. But on the moon doesn't have seasons because its orientation is perpendicular to the ecliptic. So in fact, it's really tilted maybe by about 1 degree or 1.04 degrees. So what that means is that there are craters near the south and the north poles that are deep enough that they never see sunlight. And so what they're called, we call them permanently shaded regions. So you're going to see this acronym throughout the talk, PSRs. In our field, we kind of just throw that, rolls off our tongue, PSRs, and we know what that means. It's places that are so cold that, again, never see the sun. And the idea then behind that is we also know on the moon, there's many craters. And so you have asteroids, you have comets over history have come and they hit the moon. They are filled with, they have water. Comets are, very filled with water. Even asteroids can have 10% water. And so when these bodies hit the surface of the moon, they liberate their water. The water bounces around. Most of it gets cooked off, but some of this water finds itself into these permanently shaded regions, and it can get trapped there for geologically long periods of time. And so this was the insight that Harold Urey had. And just to give a modern view of what the poles of the moon look like. So shown here on the left is a mosaic photograph of the moon's north pole. On the right is temperatures that are the maximum temperatures that you can have. And what you see is that there's some of these areas in blue. These are places that are colder than on the order of 90 Kelvin. And that's about the temperature you need to permanently trap volatiles or water if you're in a location with no atmosphere. So those would be the target areas where you might find water ice. And you can play a similar game at the South Pole here. The temperature map is focused on poleward of 80 degrees. And you can also see a number of key locations where there might be water ice. Based on temperatures, but then you still have to go and find out. So moving forward on this history, that first book was 1952. The first paper that actually made any quantitative prediction of the possibility of water ice was this famous paper, Watson, Murray, and Brown. And again, anyone in this field knows this 1961 paper. And I'm going to highlight 2 areas. Number one, this is over the right is paragraph of conclusions. And they went through their analysis and came to the conclusion that local concentrations of ice on the moon would appear to be well within the realm of possibility. So it is possible that this could be going on. They were saying that, however, it would need to be in these permanently shaded regions. And then they had a next conclusion that I like. Says attempts to determine whether water is present must await the time when suitable instruments can be placed in those dark areas. So this was 1961, very early in the space age. Almost nothing has been gone out, but anticipating the idea that you might be able to make measurements to see if there is water ice. So I want to stop there for a sec and just throw out, how would one go about telling? What kind of measurements would you make? If you were reading this paper, what would you suggest of what you could do to make measurements? Any ideas? Yeah.
I think we know more now than we did that.
Of course we do. I'm just.
Water absorbs in the infrared and can also try to detect hydrogen. It inferred it doesn't supply it.
right? So it can detect hydrogen, you can use infrared, maybe UV, anything else.
I mean, you've got to have some kind of a spectrometer
Yep.
to determine what elements are up there. And if the H and O are up there, then that's a possibility.
Right. So would you have to do it on the surface or can you do it from orbit?
Yeah, you could look for a signature, radar signature,
Radar,
laser,
yeah,
yeah.
yeah, radar, absolutely. Yeah, so you can use radar, you can use, visible light can do it possibly. UV, infrared. One area, and I'm gonna get to in a little bit, is my area of expertise, is, you can use neutrons. I'm not gonna tell you now, that's a few slides later, but just to tease you there. Is, neutrons are a really awesome way to do remote detection of water. But radar is another great way. To do it. So, okay, 1961, first prediction, there were some more papers coming up. And this now goes to the detour. And the abstract that Curtis read, there's a detour to the planet Mercury. So this is here, so this is a photograph of the planet Mercury from the Messenger spacecraft taken in, 2011. But there was a paper back in 1974, a guy named Gary Thomas, and he recognized or recalled Mercury is also oriented in the same way as the moon. It does not have seasons, so it has permanently shaded craters as well. And I just highlighted this text, and it says, if Model 2 prevailed on Mercury for a significant period in its history, we don't care about what Model 2 is. But this next phrase, ice could have accumulated in the polar regions and permanently shaded areas. As far as I know, this is the first time anyone predicted you might have polar ice on Mercury, which is fascinating because Mercury is the planet that's closest to the sun. It is the hottest planet. How on earth could you have ice at the poles of Mercury? And you really, yes.
How can you have ice deposit when there's no atmosphere?
So that's part of how this whole game plays is you can have the same way on the moon, and that's what these papers talked about, is when a comet or an asteroid comes and hits, you exsolve all the water in it. Large fraction of that water just escapes into space. But you will have the water molecules will bounce over the surface. When they find one of these permanently shaded craters, we call them cold traps. And they just trap out in that cold region. And you can do that on the moon, you can do that on Mercury. But if you have planets with seasons where, over time, you're always illuminating the poles, you wouldn't have enough time to really build up that water.
Question.
Yeah.
So the permanent shaded area, that's really talking about radiative heat. Isn't a planet like Mercury absorbing radiation and heat's gonna come up from below, right?
Not as much as you would think.
Really?
Because
It's just like soaking.
right, and parts of it, but planetary regolith is very insulating. And so if you go, in fact, on the moon and Mercury, if you go down 10 meters, you can't tell whether it's night and day. So it's very insulating material. Interesting to me. I mean, you might have the primordial heat that is radiating out, and that actually is something, but it is not that much. And so when you don't, and it's the fact that also that you don't have an atmosphere to convect heat around the planet that really helps you in this. All right, so anyway, so now we're 1974, we have predictions of water at the poles of the moon. We have predictions of water at the poles of Mercury. So now I'm just gonna set up this timeline, because I, set this whole thing up. This is a 70-year history of timeline. And I'm gonna go in parallel, bounce back and forth between the moon and Mercury. And again, PSRs are permanently shaded regions. And we have the theoretical predictions. And, the 1961 paper said, let's go and take measurements of the moon. What's interesting, the first measurements that were made were actually of Mercury. And I asked, what are the different ways that we can make measurements? It was radar measurements. And the way to think of that, the way I kind of think of it is, when you have a lot of water ice with radar, you will see very high reflectivity. And I kind of just intuitively think about when you're flying in an airplane near dawn or dusk, how can you tell where all the lakes and ponds are? They reflect differently. You just see them when you're, if you're flying. I love, when I'm in an airplane, I always try to sit by the window so I can always look out. And you can, in fact, a side story here, flying overseas, when you get on the airplane and you take off and everyone closes the windows, it drives me crazy.
Me too.
Yeah, and I was sitting in the middle and I couldn't do anything about it. So anyways, what's interesting for Mercury is the way Mercury is tilted compared to the Earth. There are seasons where you can take radar from the Earth and shine it into the poles of Mercury. And so in 1992, an experiment was done from the Goldstone radar and taking radar images of Mercury. Now, this doesn't look very impressive right here, but it turns out those reflective areas at the top are consistent with water ice reflections at Mercury's poles. Now, by itself, you wouldn't write home about this. But there was another paper in the same issue using data from Arecibo. And so if folks remember, Arecibo was a big radio dish antenna in Puerto Rico. Unfortunately, it's out of commission because they had a big hurricane and they weren't keeping it up, and it's fallen into disrepair, which is a very sad story. But these are 6 different images of Mercury's North Pole. And if you pay attention, you can see that the orientation of those reflections changes in 6 different rotational phases. And so this was published in 1992 as evidence that there may be indeed large amounts of water ice at the poles of Mercury. Now, just to jump to the chase, this is an image that was taken a number of years later, 2011, from Arecibo, where they greatly improved their ability to take data and do the analysis. This is what Mercury's North Pole looked like from that data. And all of those bright regions you see are consistent with water ice. And what you see all these craters. There's no photograph here. This is all radar data.
What's the beam width of the radar?
I don't know.
But is it the whole planet? Is it?
I think it has to be narrower, and they have to do a lot of reconstructions over time. I'm not an expert in that, but it's a great question. But when I saw this data, it's just astounded. It's an amazing data set. Yeah.
How large a area do those represent? Like how much, what's the, the diameter on some of those?
Good question. I would say, these are maybe 30, 40 kilometers across or more. They're big.
And how does that compare to the ones we were seeing on the moon?
Similar size.
Is it?
Similar size. So we got data from Mercury first before the moon, which I just find fascinating. But it's consistent with water ice. Okay, so, and in fact, it's consistent with up to 100% water ice. So ice skating rings at the poles of Mercury. All right, so now let's go back to the timeline. And now let's go to the moon. Finally, we're getting data for the moon, and it's a combination of radar and neutrons. I will talk the radar first and then do a little detour on the neutrons because that's my area of expertise. Okay, so here's radar data from the moon. This is actually taken from a spacecraft. It's harder to get in to see the poles from Earth and the moon. And so this was taken from a instrument called Mini RF that was built by APL. Yes, question.
Question, are there any similarities from the ice that we found on Mercury and the moon that we have found on like the poles of Earth as well? From like, below the sea level on the surface?
Similarities. I mean, the fact that it's water ice is similar, but I think we're so different, polar caps on the Earth. The similarities there might even be more similar to what you see on Mars. These are a different beast because these are planets with no atmosphere. So the way you accumulate is very different. But what's interesting for the moon here is, you see craters, but they're not as clear. The signals aren't as bright as you see on the moon. As on Mercury. And there really is an ambiguity where like some of these people were thinking, okay, that might be evidence of water ice, but then you see reflectivity that's on the outside of the craters. Maybe that's roughness, because if you have a lot of rocky material, that will affect radar. And so with the radar data, there was really no strong evidence for large amounts of water ice on the moon compared to Mercury, which is puzzling. And so now I'm going to go to neutron data. So I teased a little bit. How is it that neutrons can help you measure water ice? And it's really hydrogen. So this is a graphic that I use when I give a lot of talks. And really what's going on when I say neutrons is it starts with what are known as galactic cosmic rays. So does anyone have you heard of the term of what galactic cosmic rays are? What are they?
They're, high velocity, helium nuclei, generally,
It's actually protons.
protons.
Yeah. So it's high velocity protons. Anyone know where they're created? This is a cool story as well.
Sun?
Nope. Well, a sun, but not ours. Supernova. So galactic cosmic rays are created when you have supernova that go off somewhere else in the galaxy. And they accelerate these protons to very high energies. And when you go out into space, it's just an isotropic rain of galactic cosmic rays produced by a whole, slew of exploding stars. And in fact, one of the interesting stories I remember reading about the Apollo astronauts in particular, when they were going out, they would see little flashes in their eyes. And they realized this was cosmic rays producing shrink-off light, little flashes of light in their eyes. So cosmic rays are just a ubiquitous thing in the solar system. Well, one of the things they do is they hit planetary surfaces. And so this is a graphic that shows cosmic rays coming in, and then they hit the atomic nuclei and they bust the atomic nuclei up. And so atomic nuclei are protons and neutrons. And these neutrons, they can escape out into space. They can bounce around in the surface. And when they bounce around in the surface, neutrons are uncharged particles. So they're just like billiard balls. So imagine you have a whole bunch of billiard balls just bouncing around, and this is the way the moon is all the time. Now, most of the target atoms are larger than hydrogen or neutrons. So it's like a bunch of big bowling balls. So if you have billiard balls hitting bowling balls, they don't lose their energy very efficiently. But if you have a billiard ball that hits another billiard ball, everyone knows when you're playing pool and you get a dead-on collision with one billiard ball to another, what happens to the cue ball?
It'll stop.
It stops. It loses its energy very efficiently. Well, hydrogen, same mass as the neutron. When these neutrons are bouncing around and they find a hydrogen atom, they lose their energy very quickly. They get downscattered to the lowest energies. And so the signature for hydrogen is you see a decrease in the number of what we call epithermal neutrons. These are like medium energy neutrons. And it's a very, very key indicator for looking for hydrogen. And so the Lunar Prospector mission, this was how I got my start doing science. I was a postdoc at Los Alamos National Lab, and it carried a neutron detector. And so it's a detector that when you are orbiting above the planet, you can see neutrons coming off of the planet and you can measure their count rates.
What kind of a detector can see those tiny things?
So there are certain types of material that absorb neutrons very efficiently, and then they produce other, like I'll call other particles. One of them is called, these are called helium-3 detectors, and so they're just basically canisters filled with helium-3. A neutron will come in, and when it sees the helium-3, it undergoes a nuclear reaction that produces a proton and a triton that you can actually measure with your electronics.
Sort of like a photon hitting film emulsion.
Yeah, yeah.
Got it.
And so, but it's unique to neutrons. So when we flew this detector over the poles of the moon, the way to read these two maps, this is the North Pole and that's the South Pole, is the colors represent count rates. And as I said, the indicator of hydrogen is a low count rates of epithermal neutrons. Well, that's where you see these, and these are in the general regions of where these permanently shaded craters are. And the challenge with this measurement is that spatial resolution is very broad. It's not like a camera. So we can, someone asked, what's the size of these craters? The spatial resolution is broader than any of these craters. So we can't answer that. But we do know that there is, a good bit more hydrogen at the poles of the moon than there is elsewhere. And you can actually infer that there, on average, would be around 1.5 weight percent, what we call water equivalent hydrogen. And it was interesting when this came out back in the late 1990s, the press made a big deal. Water on the moon, this is fantastic. Well, even this amount is still very dry. I would estimate you could go outside, pick up any rock, and you will find at least 5 times the amount of water in that rock than you do in these locations. So, but it's still a lot more water than elsewhere on the moon, which is a factor of 10 lower Earth. Yeah, question.
Is there any way to determine the D to H ratio for these frozen water in the crater?
I would love to. I think from orbit, it's really challenging. And people have talked about that a lot. I think you need to get on the surface in one of these craters to make that measurement with a mass spectrometer. But there's some really interesting astrophysical implications. In fact, that leads to one thing I was going to talk about it later, but there's some really cool science that people have talked about just studying these regions at the poles of the moon. And it relates to the idea, I don't know if people have heard about the fact that folks go meteorite hunting in Antarctica. Has anyone heard of that?
Yeah.
Yeah, they're easy to see.
Because they're easy to see, right? I mean, meteorites fall in equal probability anywhere on Earth, but in Antarctica, it's all ice and any rock you see is almost always a meteorite. So what that means is the poles of the Earth are concentrators of solar system rocky material. And so if you want to study the history of the solar system rocky material, where do you go? You go to Antarctica. The poles of the moon are concentrators of solar system volatile materials. So it's hydrogen, but there could be carbon, sulfur, other volatile materials. And so right in these regions is a time capsule of the history of volatile materials in the solar system, which is just really cool.
What is volatile?
Volatile
It
means it's
evaporates?
stuff that evaporates very easily. And so that's why hydrogen, when you heat it up, it bakes off very quickly. And there's a whole host of elements that tend to be volatile. So one little science thing about that. Okay, so moving on to our timeline, going back to Mercury. And now, we had the radar measurements. And we actually sent a spacecraft there, and it's called the Messenger spacecraft. That was a mission that was actually built by my organization, APL. It was really awesome. Did a whole bunch of different measurements, cameras, composition, magnetic field, thin atmosphere. But one of the things they did was on Messenger was actually photograph the poles of Mercury. And so here now is a superposition of the radar images that I showed earlier. Those are in yellow, with actual photograph of all the craters. And interestingly, maybe not surprisingly, those regions of the radar brightness exactly coincide with places that we can now confirm are permanently shaded craters or regions on Mercury. So really confirming that where you saw this backscatter of radar that indicates lots of water ice is in permanently shaded regions. And one thing that's even cooler is focus in on this 30-kilometer diameter crater. So actually you're asking scale size. These are bigger than 30. So this is about 30 kilometers in diameter. And you see in that crater, there is one small radar feature, and it's also a north-facing slope. So you can imagine this might be where the sun never shines. So this was a photograph taken with the camera, and not surprisingly, you can't see into the dark because it's dark. But you can actually play some tricks where you can overexpose your pictures. And so overexpose it a little bit. I don't know if you can see this dark region of it. It's interesting. Like overexpose it more, you can see it a lot more clearly. That's where the radar bright deposit is. And that dark region is anomalously dark. And in fact, it's consistent with an organic type of compound. It could be carbon, hydrogen, other stuff rich. We don't know fully what it is, but it almost exactly coincides with the radar bright deposit and our best estimates of permanent shade. So when you pull all the messenger data together, it's pretty clear that we have a lot of water ice there. You see the radar enhancements. I didn't show it, but the temperatures in these places are colder than 90 Kelvin, which is what you need to trap water ice. I also did show the neutron data. We had a neutron detector on there, and that also was consistent with lots of water ice, and then these anomalous regions. So Mercury is just a fascinating place. All right, so now going to some of the latest measurements of the moon. So we can try similar games with the moon. So this is Shackleton crater. The X marks the south pole exactly. So Shackleton is this crater that's almost right at the pole. And this is an overexposed image of Shackleton, where you basically use light bouncing off the walls to see into it. There's nothing in here like you saw on Mercury at all. There is some hints. This is now a map from a paper in 2018, where they combine different types of data, and each one of these green points is a spot where they saw evidence that there might be surface frost, but that's in the top fraction of a millimeter. It's not anything deep down. And so there's some idea you have surface frost, but no evidence for the large amounts of water ice that you see on Mercury. There was one other experiment, I don't know if folks have heard about, it's called L-CROSS, later Lunar Crater Observation and Sensing Satellite Mission. So this was attempting to say, can we get something on the surface in some way to get an in situ measurement? And so this launched on the same rocket as a spacecraft called Lunar Reconnaissance Orbiter in 2009. And this was a pretty bold plan. And what they were planning to do was this was on the same stack as the Lunar Reconnaissance Orbiter. And then they arranged for the second stage of the rocket to fly right into one of the deep permanently shaded craters on the moon, impact, and then the spacecraft would follow in, look at the plume, and see what you see. And then the spacecraft itself would have a second impact. So this is what L. Cross saw. It doesn't look super exciting, but this little smudge here, which was blown up there, that's the impact of the shepherding of the Centaur upper stage. I remember we watched this at home and it was very exciting. And you watch the NASA stuff and you're looking for a big, a big spark or something. And it was like, huh. It didn't seem to be very exciting. But when you look at the data, and I'll grant these are a lot of the squiggly line datas, but the point is these are 3 different time steps. And this is the spectra that you're seeing from the reflected light coming off the spectra. And it's consistent with a whole load of different volatile species, H2O, CHH4, some mercury in there, it's just a whole load of stuff going on that was lifted off from this impact. And when they worked it out, at least in this one location, they were saying on the order of 5 weight percent water ice. Still not the 50 to 100% at mercury, but still not nothing. Okay, so summing up this part. So water on the moon and mercury. So mercury temperatures are cold enough to capture water ice and other volatiles. You see high concentrations of water ice and other volatiles. You see evidence for that. In the moon, temperatures are cold enough, but you don't see, 10 weight percent is actually the maximum that you might have. And I don't think we actually have that, but there's still something there. But what's interesting is that at least has been one of the hooks pulling us back to Artemis as to why the South Pole. So the NASA Artemis program is sending humans back to the moon. There's a landing site near the South Pole. That's what they're targeting. And this picture shows an oblique view of the South Pole. This is Shackleton Crater that I showed earlier. And the South Pole is about right there. And there's really 2 very valuable resources that may be here. Number one is the volatiles, water ice. It's still not clear if the amount of water ice on the moon is actually enough to be useful. Scientifically, there's some really cool things regardless, but the jury's still out. But there's also the resources of sunlight. So you have permanently shaded craters, but there's also places nearby on these rims that are almost permanently lit. 80 to 90% of the time in these ridges, you have sunlight. And when you're on the moon, that's a really valuable resource because trying to survive the lunar night, if you're on most of the moon, that's a very challenging thing because 2 weeks out of every month, you're in deep dark and it's super cold. Whereas if you have some assets landed here, you can be using solar power for 80 to 90% of the time, and you might be very close to water ice resources. So that's the motivation for going to the moon's South Pole. And I'll finish up with a few slides on the Artemis program. So I borrowed these from my colleague at APL. And these are the 4 astronauts that are slated to do Artemis 2. I will note Christina Koch, I think that's the way to pronounce. She's a former APL engineer, interestingly, who got selected to be on the astronaut program. And so Artemis 2 is the next human mission on this program. It is not going to land. It's going to do an orbit around the moon to prove out a lot of the hardware, which then will lead up to the Artemis 3 mission that is planning to land at the South Pole. And so I'll finish up here with this really nice video that illustrates a lot of what I was saying in the talk. So we're going down and flying to the moon's South Pole. And what you will see is the day seasons, and this really illustrates how you can have some of these permanently shaded regions. You're going through a whole day cycle, and there's some places that are always in shadow. And then finally, these locations here, I think, are the target sites for the landing. They haven't been fully selected yet, but the current ideas are a combination of where might there be the hydrogen or the water ice combined with where it's a lot of the sunlight. So anyways, that's the talk and the pulling together of the Simon story.
So if I may ask some questions, Artemis, you know anything about it?
I will do my best to answer.
Okay.
Yep.
This is fascinating. I'm fascinated by that. You have not sent Artemis 1 yet, right?
Yes.
But do you know the time frame for Artemis 1?
I think, wasn't that the
It's
one?
launched.
Yeah.
That's the one I already launched.
Okay, 1's just launched, 2
We're waiting. I think that's 2026 is the
April.
current launch date.
April, thank you. And do we have a time frame for 3?
28, I think is.
Okay. And then I'm just wondering now, competition. India, China.
Yes.
Do you think that they are going to get, I don't think India will, I think they're still, they don't have the research to work with China. You think they're gonna get there first?
I don't know if they're gonna get there, but it's gonna be a good race.
Because why?
China is being very impressive in how they are pursuing their lunar program. They are being very systematic. In fact, of all the attempts to land on the moon in the last 5 years, China has the absolute best track record. They've returned samples from the moon twice now. And so and I also know I'm still working on potential future measurements to understand the water at the poles of the moon with better spatial resolution. The Chinese are attempting similar things. So, yeah, it's definitely a race. And yes.
So just to go back a little bit to you were talking about the detection methods.
Yeah.
And you were giving amounts in weight percent. And so with the various detection methods, like how deep are you able to detect?
Great.
Right? You know, because really what you're getting, radar, you're getting a reflection. So really you're looking at area. You don't really know, how thick that would be.
Right. So it depends on the detection. So starting from the top, if you're talking visible light, infrared, UV, it's top tens of microns. So when I was showing some of those detections of frost, I think that's real, but that's just superficial. The neutrons, they are integral down to tens of centimeters. So, macro this depth, because the neutrons penetrate and come out from that depth. And in fact, there are ways when you dig into some of the neutron data, there's hints that you actually might have some layering involved where, maybe the top few centimeters are drier material, below that is wetter, so to speak, so very dry. But then you talk to some folks and there's some ideas that, the top meter to 2 meter might be really dry, and down below that on the moon might be having a lot more water ice. There you might need to employ some of the radar techniques.
So if you go to the mission you talked about where they, basically dropped a bomb on the crater, right? And
Yeah.
analyze the dust plume. How deep did that material?
Probably 10-ish meters.
Okay,
So, yeah,
and what did that say?
well, you can't tell any layering, and
Right,
so
right.
this, you know, 5 weight percent,
Include a greater depth.
yeah, 5 weight percent down to that. And so there's some ideas of, well, you know, again, maybe the moon seems dry because it's, you know, it's a lot more wet below that, and we just haven't been able to sense it.
The tens of meters we didn't get dramatic.
That's true, we didn't get mercury levels. Yeah.
Yeah. We're not minuscule amounts of water.
Huh?
Minuscule amounts of water.
Yeah, 5 weight percent.
Yeah.
Yeah.
Is there a theory of why Mercury has such a higher weight percent than water on the moon?
Yeah, there are theories, no one really knows. In fact, that's one of the big mysteries is, you know, why Mercury a lot and why the moon it isn't. One convenient way, and I don't necessarily like this, is it may be on Mercury, you had a recent impact that just put the stuff there, and there is a crater that's kind of nearby that could explain it, and so, you know, maybe it just hadn't had time enough to cook off. Even in permanently shaded craters, you do lose some amount of water, so that might be one of it. There's other ideas out there, but to really answer it, I think you need to, you know, you almost need to get on the surface at the moon and at Mercury, look at isotopics, you know, get more detailed measurements.
So, correct me if I'm wrong. Does the Grand Tech model suggest that Mercury did not form where it is, it was further out? And so, as Jupiter is doing its migrating, all hell is breaking loose.
Right.
Perhaps that would lend to cratering rates. Is that right?
I'm familiar with the Grand Tack model. I don't remember what that predicts about Mercury per se. I'm not sure if that would have a lot of bearing on this problem necessarily, though. Yes.
Can you go, David, can you go back to the launch vehicle there, that picture you had of the Artemis launch vehicle?
That one?
On the launching pad.
Yes.
Okay, so it basically looks like an Apollo type rocket with two like Martin Marietta Michoud kind of rockets attached to the sides, but it
Right.
looks like a Saturn V, is it?
It's not a Saturn V, that's the SLS I think, and so.
But
I don't know.
but as far as landing again, they'll have a hookup, a lunar service module, and they'll basically do an Apollo type of thing. Right?
Yeah, I think that's sort of what you see here. Yes.
Question. Considering what he said, I'm just kind of curious. Once they get off the moon stuff, like once they leave, how can we predict where they're gonna land back on Earth? And is there gonna be some sort of quarantine type, like certain time of quarantine, like they did on the Apollo missions?
Interesting. So in terms of predicting I think the orbital dynamics is mature enough that they target where they want to land on the Earth. As far as quarantine, I would suggest probably not, because even the later Apollo missions didn't need to quarantine. It was only the first couple. And they realized that the moon was pretty darn sterile, so not a problem. Yeah, sure.
I just want to follow up, you know, when I think about frost or ice, right, I think about that's an accumulation of water molecules.
Yeah,
right?
yeah.
But I wonder, you know, you get different detection methods, how much of it is water molecules incorporated in a rock sort of at a molecular level?
Yep.
And how much of it is actual, you know, water, ice, or frost? And is there a way to differentiate that?
Yes, and in limited ways, so, if you're looking at the superficial frost, if you're looking at UV infrared, there's different, molecular vibrations, like if you're detecting, I think. You're detecting a 2 micron band, might be getting the number wrong. That's an indication of actual water. Whereas if it's a different band, it might be more of an OH, which would be more of a molecular, not water ice. And so there's those areas, ways you can go about detecting it. The neutrons, it's only
I
hydrogen.
just tell you that there's hydrogen.
It's just hydrogen. You can't tell. You have to infer, you know, if generally speaking, if you have more than a few weight percent of what I call water equivalent hydrogen, odds are it's probably water ice. But, you know, there's other places on the moon where we're detecting, I don't know, a few hundred parts per million hydrogen. That's almost certainly not water ice. And we can only detect the hydrogen.
The reason I ask is, you know, I wonder if maybe on Mercury, perhaps different types of soils, if you will, you know, are exposed in places and might have different interactions with water.
In fact, in those polar regions, that's almost certainly
I'm
the case.
completely ignorant, I know.
Yeah, no, it's
about
almost,
Mercury,
there's
so-
some really cool chemistry going on at Mercury's poles.
Right, whereas the moon, it's pretty homogeneous.
Yeah.
Just one more follow-up. Took 17 before we got Harrison Schmidt on it. He's sending a geologist this time.
I have no idea. But, by the way, Harrison Schmidt is still doing science.
Oh, I know, he's an amazing guy.
And I've gotten to know him over the years and I highly respect him. When I was a younger scientist, he would show up at the lunar and planetary science conferences. And he would sit in all the sessions, just interacting. And what was really cool was you would have young students coming in and, you know, they're giving a talk about, you know, they did this analysis with Apollo 17 sample or something like that. And it's Q&A time. And Jack Schmidt says, very nice talk. And when I picked up that sample, you could tell the students were just like, oh my goodness. It's so cool.
One more question, so you talk about water ice on each poles.
Yeah.
Do you think that in the far future, that if we humans are able to settle on the poles, and if we are to discover like larger pockets of carbon, do you think that, you know, we would start putting like, you know, like kind of like human pods where we kind of like dig out and do some like, you know, investigating like how deep do the carbon piles go? Like, do they go further down into the crust, or do they go all the way down towards the core?
I don't think anyone's gonna get down to the core, but, you know, the sort of general gist of your question is, you know, could we settle people there? And is, you know, the big question, is that amount of stuff there useful or not? And useful in what way? I can say there's a lot of work going on in a field called in situ resource utilization. It's basically, how do you live off the land? And the way you answer that is very different if you're on the moon or if you're on Mars. And it's challenging. For the moon in particular, we don't know. There's still a lot of work we need to do to figure that out. And so, but having said that, that's actually why we're targeting the South Pole, is that at least has some possibility that there could be some, you know, useful material that you can live somewhat off the land.
Will we also be just like looking for some sort of like, if there's water, will we be looking for some sort of microbial life as well?
People have talked about it. There's papers out there. I think on the poles of the moon, you're not going to find it because the radiation is pretty, you know, it's kind of harsh. You know, there could be some low-level chemistry going on as initiated by cosmic rays and stuff like that. But as far as any detailed, you know, prebiotic materials, probably not.
What's the status right now of moon treaties to keep it de-weaponized and all that kind of stuff? Are you up on that?
Not a whole lot, unfortunately.
But you know, like, do you have the basic outlines? Like there is one for Antarctica, so is there one for the moon?
The Artemis Accords.
There's the Artemis Accords, and that gets political pretty quickly between us and the Russians. And a lot of it is just how do you make use of it? What do you do if you have, you know, let's say China's on this place in the South Pole and the United States, how do you interact? What if you have an emergency? What do you have interoperability of interfaces and things like that? So it's, you know, it's not only just weaponization, how do you work together? And there's a lot of people working on those details pretty deep. And so I don't know all the answers to that. That's not my area of expertise.
Is the information flow between the Chinese scientists looking at they landed on the far side, right?
Right.
And what we're doing on the South Pole, is there free information?
There's I think it's called the Wolf Amendment that prohibits US funded scientists to work directly with Chinese scientists on a one-to-one basis. You can work as part of multilateral groups. And so there is some flow of information. I know there's actually more flow of information with the Europeans and the Chinese. I have some colleagues that were part of one of the Chinese landed mission. And so there is some, you know, but you can't avoid politics, unfortunately.
So I think people are excited about man missions.
Yes.
But just your opinion, scientifically, no politics, no nothing, right? Is there anything that a man mission going on the South Pole can do that we're going to unmanned missions do not do probably cheap?
Good loaded question.
Politics aside.
Politics aside, yeah, I think the Mars rover is actually give an excellent case study for that, where they've driven, you know, many tens of kilometers, but they've taken a long time to do it. With a human mission, you could probably accomplish what the Mars missions did in a few weeks. So, you know, put that, you know, that's part of the trade-off there. And, you know, when you have humans in the loop, you can do many things that when you're doing the, you know, robotic craft just takes so long. So, yeah, you can do a lot of it. And is it worth it or not? I would argue maybe that's a good place to finish off here. You know, there's the inspirational aspect, space exploration. So I was born in 1968. I grew up on Apollo. I remember the Apollo 17 launch. It was at that time I wanted to be an astronaut.
So did I.
Yeah, I can't count, I lose count of the number of people, even colleagues, that's what motivated them to do what they wanted to do. I applied twice, this got in the way, and I wasn't good enough anyway, and my wife is glad for that. But that was the inspiration. That's why I'm doing what I'm doing now, because I actually ended up meeting Jack Schmidt once, and I said, I want to be an astronaut, and what do I do? And interesting, what he told me, he said, you know, go be a scientist, and, you know, that's the way you can go and be involved. And so that's what I did, and, you know, here's what I'm doing. And so I think there's that aspect of space exploration that I do think is important, because it inspires, it's
Perhaps in the long run, it can cause a shift of more dollars into science research.
That's
As
good.
opposed to taking dollars from elsewhere.
Yeah, yeah. I mean, the other thing I would argue is space exploration is a great bringer together of people. And I think that's really important. I work with many international colleagues. I just came back from Japan from a mission that we're working with the Japanese for. And it breaks down barriers in an amazing way. Even when we have all this politics in the way, and it doesn't matter what your politics are. It breaks down barriers.
All right. I guess we got time for one more question from Evan.
Good question. I don't know if this, I don't know if it's gonna make any sense, but if we're talking about like space travel and like outside of our solar system. When we, obviously, we know that there are exoplanets and with other stars.
Yeah.
Do you think that like far in the future, if we ever get to like traveling outside of our solar system, we will be able to discover like moons, moons of, exomoons that have similar, that are similar to what we see on Mars and Mercury and the moon?
It's hard to predict, especially about the future. I think 50 years ago, we would never have predicted detecting exoplanets. But traveling that way as a physicist, I think that's ridiculously hard.
Or even satellites of asteroids.
Yeah, so.
All right, well, I think we're gonna call it good now, and that way Dr. Lawrence can go to bed.
That's the brought stickers for you all.
Thank you very much.
Thank you very much. We're gonna have a break.
Yeah, we're gonna have about a 10-15 minute break, and Dr. Lawrence brought some of his mission stickers. Help yourself. Please sign in.
The stickers for this is for our instrument that's on the Japanese Martian moon exploration mission, and our instrument is called Megane.
Hello.